Okay, so it's time to do the two Doppler effect questions that you had last night for homework. We had done number 1 from the sheet in class yesterday, so we have number 2 and number 3. Number 2 says the frequency of a car horn is 505 hertz and the temperature is 29 degrees Celsius. So 505 hertz is your F and 29 degrees Celsius. We take that 29 degrees Celsius and we put it in our speed of sound equation. 331 plus 0.59 times t. And when we do that, we get our speed to be 348.11 meters per second. Okay, we go back to the question and it says, what is the apparent frequency of the horn if the car approaches a person standing on the side of the road at a rate of 20 meters per second? So 20 meters per second is the source, and the person is standing on the side of the road, so their velocity, the observer, is 0. It's approaching, so it's going to be F times V plus VO on the top over V minus VS on the bottom. The VO, the observer speed, goes to 0. So this is going to be 505 hertz times the speed we just found, 348.11 meters per second, divided by, on the bottom, 348.11 meters per second minus the 20 meters per second. And then you punch that in your calculator and you find out that the apparent frequency that the observer will hear is 535.78 hertz. Okay, try it to make sure that you can get it. Then we go on to part B. What is the apparent frequency of the horn after the car has passed the observer at the same speed? So now it's going away from the observer. It's receding, so it's going to be V minus VO on the top and V plus VS on the bottom. The observer is still not moving, it's still 0. So the top is still going to be 505 hertz times 348.11 meters per second. Temperature hasn't changed, so the speed of the sound hasn't changed. And on the bottom, 348.11 meters per second, this time plus 20 meters per second. Punch this into your calculator and you will get an F prime, an apparent frequency of 477.56 hertz, and I'm rounding to 2 decimals here. The C part of the question says, what is the frequency drop as the car passes the observer, the difference between them? So you just subtract those two numbers for C, and when you subtract those two numbers, you should get something like 58.22 hertz, give or take a few decimals. Okay, so that's it for number 2. Number 3 says, a person in a car is driving at 90 kilometers per hour towards a train whose whistle is blowing at 444 hertz. So the frequency of the train is 444 hertz. It says the temperature is 24 degrees Celsius. So again, we're going to take that 24 degrees Celsius and we're going to fill it into our speed of sound equation. And when we do, we end up getting a speed of 345.16 meters per second. Now it says the person in a car is driving 90 kilometers per hour. That's the observer. The car is not making the noise, the car is hearing the noise. So the speed of the observer is 90 kilometers per hour, which when you change it to meters per second will be 25 meters per second. In part A, it says nothing about the train moving. We have to assume the speed of the source is 0 for part A. It changes in part B. Okay, so the car is approaching the train. So we will do F prime is equal to F, V plus VO on the top, V minus VS on the bottom. Okay, now we fill our numbers in, 444 hertz. The speed of sound, 345.16 meters per second. I lost my 5. Plus this time, the 25 meters per second. and there is no speed of source, so that goes to 0. And so on the bottom will just be the 345.16 meters per second. And so when you do the math here, you get an apparent frequency of 476.16 hertz, higher than what the original one was, which is what it should be, because it's actually approaching, so you should hear a higher frequency. Part B says the train now leaves the station and heads directly away from the motorists at a speed of 18 kilometers per hour. So now the car is approaching the train going 25 meters per second, but the train is going away from the car going 18 kilometers per hour, which if you switch to meters per second is 5 meters per second. Yesterday we talked about using relative velocities in this case, because this is the speed of the observer, this is the speed of the source. So it's the same as saying this, because one's approaching and the other is receding. So it's the same thing as saying that the source is stationary and that the car, the observer, is approaching at 20 meters per second. And now you use the approaching equation again. So F times V plus VO over V minus Vs. And if we're using relative velocities, the Vs goes to 0. 444 hertz, 345.16 meters per second, plus 20 meters per second. And then that's going to get divided by 345.16 meters per second. And when you do this, the apparent frequency is 469.727 hertz. That is bigger than the original frequency, but smaller than the one when the train was stationary and the car was approaching at 25 kilometers per hour, 25 meters per second. That should make sense. It's not approaching it as quickly, so the apparent frequency should not be as big. Okay, so hopefully these made sense. You were able to do them, and that you can do the 3 questions on Doppler effect on your assignment that was due today, which you'll now hand in tomorrow. See you very soon.